Hello everyone. Today I'm going to talk about a review on the exploration of red phosphors for the fabrication of phosphor converted light emitting diodes for indoor farming. The work has been carried out by Dr. Jyoti Rawat and me, that is Dr. Sudeshna Ray. We are from Advanced Materials Research Center, Faculty of Science, Ravindranath Tagore University, Bhopal, India. So let me talk about first the World Population Prospect 2019 published by UN Department of Economic and Social Affairs reports that the world population could reach its peak around the end of the current century at a level of nearly 100 billion. And this increase will need to be accompanied by the increase in food production, and that too in a world where the land for farming land is becoming an increasingly scarce resources. To address this problem, a relatively new agricultural practice known as vertical indoor farming, that is VIF, which relies on height rather than width to generate agricultural production, has emerged as a form of sustainable cultivation of plants. This is the world population growth trends. Well, there's you can see the fascinating pictures of vertical indoor farm in Japan, in Singapore, in Chicago, in Netherlands. This harnessing this vertical indoor farming technology, indoor farms are attracting significant attention in various countries. Light provides energy for suitable ambient temperature and photosynthesis process. We all know that sunlight is necessary for this photosynthesis and plant growth and development. And here in vertical indoor farm, LEDs are used as the artificial sun. That is, we are simulating the sun by LED, light emitting diodes. Okay, the light is not only the essential energy source for photosynthesis but also affects several development processes including seed germination, flowering, fruiting and other morphogenesis in plants. To supply the energy needed for plant growth, LED has become the primary artificial light source with the following advantages like high brightness, good reliability, excellent adjustability, low power consumption and long lifetime compared to traditional forms of artificial lighting such as metal halide lamps, fluorescent lamp, incandescent lamp as well as high pressure sodium lamps. So LED are advantages over all these traditional artificial light sources. So let me see the important that is we all know that leaves look green because they do not absorb the green light. They absorb blue as well as red light. Here in this picture we can see the chlorophyll B and chlorophyll A absorption, that is optical absorption spectra, and interestingly we can see that they absorb the red light ranging from 600 nanometer to 700 nanometer wavelength. This red emission, however, from aluminium, gallium, indium phosphide red LED chip is comprised of a narrow emission spectra. Well, in the contrary, we can see the chlorophyll has a broad absorption in the red region. So here comes the role of phosphor converted LED, because the red emitting phosphor that is excitable by blue light can give a broad emission spectra because europium 2 plus, cerium 3 plus, they are all involving their d electron emits. Their emission spectra is a very broad emission spectra. So that can be absorbed by chlorophyll. So strategically, by the help of phosphor converted LEDs, we can fulfill the purpose of the chlorophyll absorption in the red region, which is having, again I am highlighting, a broad absorption in the red region. And we are elucidating the solution synthesis mediated approaches for the synthesis of this high efficiency red emitting, just like silicate, aluminate phosphors. Mainly we are discussing the silicate phosphors in this talk. Okay, the advantages of silicate phosphor, inorganic oxides, because of the stable crystal structure normally used for LED phosphors, and more than 18,000 inorganic crystalline compounds containing silicon as a common element are found in the Earth's crust. So, search for the new phosphor. Now, the first mineral was Bologna stone that was discovered in 15th century. From that, when actually these mineral-inspired methodology is developed by Professor Kakihana in Tohoku University when I was doing my postdoc. At that time, I was trained with this kind of technique, which is a unique method for developing new phosphor from the minerals. So what is the process is very easy, that we need to check from the American Mineral Society database the latest reported mineral and substitution of one element of a particular composition like barium, strontium, calcium by similar size isovalent ion, that is either transition metal ion or rare earth ion, that is europium 2 plus mainly we are using. And important point, substitution of the transition metal ions in the host composition by similar sized and isovalent ions like iron 2 plus, copper 2 plus substitution by Mg2 plus and Ti4 plus substitution by Zr4 plus has to be taken place, because these ions are detrimental for the luminescence. So these are the process we need to search like this. And from this American Mineral Society database, we are just giving an example that we have developed a new phosphor. Now the interesting thing is that what is the specialty in our work, that is silicate are highly insoluble in nature. So making a water soluble solution of silicon is difficult, and for solution synthesis, the way we can maintain the stoichiometry of the compound, and because of the that the dopant get anchored properly into the host, giving high luminescence efficiency, because after all the efficiency, luminescence efficiency matters for this device fabrication. Here the Japanese group has developed a process in which TEOS along with propylene glycol in acid catalyzed reaction makes propylene glycol modified silane, that is called PGMS, which is miscible with water at any ratio and non-volatile in nature. Silicate phosphor can be synthesized by an aqueous solution method by using PGMS. Now, this is the pictorial representation of parallel solution method, in which this process we can make a lot of silicate phosphor and then screen and which one is luminescence. We can go for the XRD, check the phase purification or phase identification, and then accordingly we can tune our synthesis methodology by using flux to enhance the luminescence efficiency. So thank you very much for your kind attention.